Hello and welcome to another video. This time we're going to be looking at serial UART interrupts. Every time new data arrives on the serial port, we'll get an interrupt and we can deal with it. In this video we're going to connect our PC to our Agon via a serial connection. We need a ground wire connected and the receive wire connected on the Agon. These are the pins on the UEXT connector, if that's more convenient. So let's take a look at what our program's going to do. On the right I have a terminal program on my PC which will send data into the Agon. And on the Agon we're going to run our program. What we've set up is a buffer of 24 bytes of data, and at the moment each of those bytes is filled up with a space, that is ASCII character 32. Our program is continually redrawing this list, and I've deliberately slowed it down so you can see what's happening. However, whenever data is sent in on the serial port, we're going to get an interrupt, and our interrupt routine will deal with that data immediately, even if it was halfway through drawing the list. So if we type in and send something, it's filled in the first 5 bytes of that buffer. You'll notice also that the carriage return, number 13, we've simply presented as a question mark because that's an unprintable character. So let's take a look at the code. The first thing that you'll see is that we have a few constants set up. One is for the ID of the receive buffer on the UART, which is D0, and we've set up some data for the configuration of the UART port. In this example, we've set the speed at 9600 baud. 8 data bits, 1 stop bit, no parity and no flow control. And here's the important bit here which makes it different to using the serial port at other times, and that is that the interrupt bit, the last bit here, is set to 1. And that means that an interrupt will occur every time a byte of data is received. We must make sure that we're in interrupt mode 2, and we're going to store a count of the number of bytes which have come in. We'll make sure the cursor is not displayed, and we'll call a routine which resets the buffer, so that in case we run the program a second time, the buffer is cleared. We'll clear the screen, and then we'll open up the UART port. This routine we'll go through in detail shortly. And so our main loop program is doing 2 things. Firstly, it's checking to see if we press the escape key, and if so, we exit. And the other thing it's doing constantly is updating that display. In order to update the display, we tab to 00 and print the title at the top, the count, the number of bytes received. We then print in decimal the number of bytes received so far. We can see that at the top here. At that point we had 13 bytes currently received. We're then going to put in 2 line feeds to separate it slightly. We're going to load DE with a beginning of where our buffer is in memory, and that's an address here. And we're going to load B with 24 because we're going to go around the loop 24 times looking at the 24 first bytes in that buffer. And so the first thing we do for each line is we clear that line. We've then got a small delay so we can see what's going on. We're going to get the first byte from our buffer and then move our offset along one for next time. We're storing some of those registers because we know the next routines might destroy some of them. We'll then check whether that character is below 32. That is a non-printing character. And if it is, we'll just replace it with a question mark. Then we're going to print our character. We'll print an extra space to make it neat. We'll get back our original byte that we had and print it in decimal. Next we do another line feed, and get back our pointers and our counter. And then we go around this loop again 24 times. And that routine is what's going on all the time. Printing count at the top with the number and every byte that we've got in our buffer. Next we've got the UART routines. First we open up the UART with a MOS call 15 and with a UART structure defined here, and that we'll look at in a moment. We need to set HL with the interrupt service routine we want to call, and then we'll set the interrupt vector number for this routine. So here's the chart of interrupts that we've looked at before, and in this time it's 1A, the UART1 vector that we're interested in. And the MOS call here 14 will set up that interrupt. We load HL with the address of our buffer and define the UART buffer position with HL. So we've now reset a pointer to the beginning of the buffer. As we defined in the constants above, the UART structure contains all the information that's needed for the UART to be defined. And here's the interrupt service routine. Firstly, we disable the interrupt to stop anything else interrupting this. And we store the registers that we're going to use so that it can be restored afterwards. As we received an interrupt, we know for sure that there's a byte ready to be read. So this command will read that byte into A. We'll get the latest buffer position and then set that byte with the new one we've just received in A. We'll increase the pointer to that buffer position and store that again for next time. We are then going to get the byte count, increase it and store it again. Restore the registers, re-enable the interrupts, and then we can return. In this example, I've connected a MIDI keyboard to the Agon's UART port. I've also removed the delay which we had before. At the moment there's no data, but you'll see for something like a MIDI keyboard, it doesn't send one byte at a time. For every key press or every key release, it sends 3 bytes. As I press the key down, we get 3 bytes, and when I let go, we get another 3 bytes. If I choose a different key, the same thing. So there might be times where you want to deal with multiple bytes in a chunk. By putting that serial data into a buffer, you can then deal with it when you've got the correct amount. So in this case, in order to play a note, we need 3 bytes of information, and so can only make that note happen when we've received all 3. Having a buffer means that we can read 3 and then move on into the buffer until we find the next group of 3. So as you can see, it's easy to grab bytes from the serial bus as soon as they arrive. You can store them and then deal with them later in your own time.